Good day, everyone. Today, my teammate and I will be presenting the step-by-step design of analysis of the digital filter from our assignment covering the FIR filter section along with their MATLAB implementation. So for the group members, it will be me, Arif bin Abdul Aziz, and my friends, Madzhar Hakimi. So for today's assessment, I will be covering assessment 1 and MATLAB. Meanwhile, my friends will covering assessment 2. Starting with assessment 1, part 1, we analyze the target magnitude response cache for our low pass filter. The graph highlights three distinct zones: the pass band, the transition band, and the stop band. The pass band age, frequency FP, is set at 1 kHz with permissible ripple boundary, while the stop band age, frequency FS, begin at 1.5 kHz. The negative 3 decibel cut-off frequency FC is located right in the middle at 1.25 kHz. In part 2, we perform a parameter derivations, normalizing our frequency against a peak frequency of 5 kHz. We find the normalized passband H omega P equal to 0.4 pi and the stop band H omega S equal to 0.6 pi. This yield a transition with delta omega equal to 0.2 pi. The ideal normalized cut-off frequency is computed as omega C equal to 0.5 pi. Based on the required stop band, intonation, a Henning window is selected. Using its specific window equation, the required filter order is determined to be n equal to 32, which gives us a center of symmetry delay alpha equal to 16. We then split the ideal impulse response HDN into two conditions, a central midpoint value of 0.5 when n equal to 16, and a sampling function mathematical form for all other value where n x equal to 16. For part 3, we calculate the final causal filter coefficient Hn by multiplying the ideal impulse response by our Henning window function, Wn. Here, we evaluate localized samples to show the mathematical progression. For instance, at a center symmetry point where n equal to 16, the coefficient resolves to exactly 0.5. Moving one step over to n equal to 17, the calculation yield approximately 0.3153, while at n equal to 18, the calculation drop precisely to 0.
For assessment 2.1, we transition into designing an analog FIR filter. First, we calculate the selective factor K by finding the ratio between the passband and stop band frequency, which gives us 0.6. Next, using the passband and stop band attenuation specification, we compute the discrimination factor D to be 0.2237. Plugging these two critical factors into the Butterworth order formula, we determine that the filter order n must be greater than or equal to 2.93, meaning we choose as a standard third order filter. For part 2, we pinpoint the exact analog cutoff frequency omega C for our Butterworth filter. The value is bounded by a straight inequality range determined by our passband and stop band constraints. Evaluating both sides of the inequality give us a tightly controlled range between 0.3345 and 0.3384 radian per second. Averaging these values give us a final operational cutoff frequency omega C of approximately 0.3362 radian per second. For part 3, we map the poles of our system to construct the transfer function HAS. For a stable system, we look for poles strictly on the left half of the S-plane. Using the angular spacing equation for n equals to 3, we compute three poles, a purely real pole S1 at negative 0.3362 and a complex conjugate pair S0 and S2 located at negative 0.1681 plus minus J 0.2912. Multiplying those pole factors together yields the final polynomial expression in the denominator, giving us the completed third order analog transfer function shown here.
To finish up, we validate our FRI design using a MATLAB script. The code loops through our indices to generate the window impulse response, applying an if-else block to handle the unique midpoint condition. Figure 1 displays the symmetric time domain Henning window shape alongside its decibel frequency spectrum. Figure 2, visualize the discrete impulse response coefficient Hn and the corresponding low pass filter discrete function response Hk. Figure 3, confirm our success by plotting the absolute magnitude response and the smooth disable roll-off of the final low pass filter, proving it's meet all its design goal. Thank you very much, and that's all from us. See you next time. Bye-bye.